So, what happens if you give a team of AIs a huge, complex software project and then you just walk away? Well, that's pretty much exactly what researchers at Anthropic did in this absolutely groundbreaking experiment. Let's get right into it. So, the question they were trying to answer, and it's a big one, was this: could a whole team of AI agents, working completely on their own, with zero direct human handholding, build something as ridiculously complex as a compiler, right from scratch? And look, this wasn't just some simple coding test. No way. This was designed to be the ultimate stress test for AI teamwork, to see if they could actually collaborate on their own. The whole idea behind this is something they call agent teams. Basically, what that means is you have multiple AIs, in this case, a bunch of Claude instances, all hammering away on the same code at the same time, without a human looking over their shoulder. So you got to think of it less like an AI co-pilot helping one person and more like a fully autonomous software development team. And the goal they set? It was monumental. They got a team of 16 Claude agents and told them, build a C compiler in Rust. Now, for anyone who doesn't know, a compiler is that essential piece of software that turns human code into something a computer can actually run, and building one is notoriously hard. But their target? Oh, it wasn't just any compiler. It had to be good enough to compile the entire Linux kernel. Yeah, one of the most complicated pieces of software in existence. Okay, so how in the world do you even set up a digital workshop where 16 AIs can all code together around the clock without getting in each other's way? Let's take a look at how they pulled it off. The engine that drove this whole thing was surprisingly simple. It was basically just an infinite loop script. Seriously, as soon as one AI agent finished its task, the loop would just go, okay, next, and assign it the next thing in the queue. This created this relentless 24/7 system of autonomous work. They never stopped. But wait a minute, with 16 AIs all coding at once, how do you keep them from just tripping over each other and overwriting each other's work? Well, they came up with this really clever system using Git. So an AI would first take a lock on a task, basically by creating a little file that said, I got this. Then it does its coding, pulls in any new stuff from the other agents, and merges it all together. And then finally, it pushes its changes and releases the lock so someone else can work on it. And what's amazing is that Claude was actually smart enough to handle all the tricky merge conflicts all by itself. Okay, so this whole experiment taught them some really fascinating things about what it takes to manage a team that, well, isn't human. And here's the absolute key insight. You just can't manage an AI agent the same way you manage a human programmer. It just doesn't work. The entire environment, everything from the tests, the feedback, the error messages, it all had to be totally redesigned for an AI's mind, not a human's. And this slide just shows that difference perfectly. You see, a human can look at a long, messy error log and figure things out. But for an AI, all that extra text just pollutes its context window, which is kind of like its short-term memory. It's just noise. So instead, the AI needs super concise, one-line errors. It doesn't need a friendly, oops, something went wrong message. It needs a clean, machine-readable error code. Everything had to be optimized so the AI could figure out what was going on in an instant. But then they hit a wall, a big one. When it came to compiling the Linux kernel itself, this single massive task, their whole parallel system just fell apart. All 16 AIs would find the exact same bug, and they'd all try to fix it at the same time, basically overwriting each other's work. It was chaos. They were completely stuck. The fix for this was just ingenious. What they did was use a standard human-made compiler, GCC, as a kind of oracle or a cheat sheet. So the system would randomly compile some parts of the kernel with GCC and other parts with the new AI compiler. By comparing where things went wrong, they could pinpoint tons of different isolated bugs, and that meant each agent could be given its own separate bug to fix, getting them all working in parallel again. Problem solved. And this new approach unlocked something else really cool: specialization. Once they got that parallelism working again, they could start assigning specific jobs to different AIs. So one agent became the code refactorer, just going through and cleaning up messy code. Another was the performance optimizer, trying to make things run faster. They even had an AI code quality critic, whose only job was to look at the code and suggest ways to make it better. It was a real team. All right, so after all that, after this ambitious 2-week-long experiment, what did they actually get? Let's dig into the results. First up, the cost.
The total bill for API calls over those 2 weeks came in just under $20,000. Now, that's not nothing, for sure. But think about it. That is a tiny, tiny fraction of what you'd pay a team of human software engineers to do a project this massive.
And what did they get for that money? Well, the final compiler the AIs built was a staggering 100,000 lines of Rust code. And that took nearly 2,000 separate sessions with Claude, all running completely on their own inside that relentless infinite loop. And the crazy part is, it worked. The thing was astonishingly capable. This AI-built compiler successfully compiled a bootable Linux 6.9 kernel. And not just that, it also managed to compile other huge open-source projects, things like QEMU, FFmpeg, and even databases like SQLite and Postgres. And of course, the moment we've all been waiting for. It passes the ultimate geek litmus test. Yep, it can compile and run the original Doom. But we gotta be clear here, it's not perfect, not by a long shot. The compiler has some very real limitations. It still has to kind of cheat by calling out to that human-made GCC for some of the really tricky parts. The code it spits out is also slower than GCC's, even a version of GCC with all its optimizations turned off. And the Rust code itself, the researchers called it reasonable, which, isn't exactly a glowing review from an expert. So while it's an incredible proof of concept, it's not about to replace production compilers tomorrow. So what's the big picture here? What does all this really mean? Well, this experiment points to a future that is, frankly, both incredibly exciting and maybe a little bit unsettling. What we're seeing is a really fundamental shift. We're moving away from AI as just a helpful co-pilot that gives suggestions to a human programmer. Instead, we're looking at AI as a fully autonomous developer, an agent that can take on and manage a massive, complex project all by itself. I think the lead researcher on the project, Nicholas Carlini, he really summed it up best. He said, "While this experiment excites me, it also leaves me feeling uneasy." And that captures it perfectly, right? This progress is happening so much faster than anyone really expected. And that opens the door to all sorts of amazing possibilities. But it also brings a whole new set of risks. And that really leaves us with a huge, critical question for the future. As we start to rely more and more on these autonomous systems to build the very software that runs our world, what happens when something inevitably goes wrong? If an AI team builds our software, who exactly is responsible when it breaks?